Welcome back to our tutorials on control system. Today we will discuss the analogy between the electrical and mechanical system. So let's start. At this instance, I will try to apply the different concepts related to the electrical and mechanical systems to make the analogy between them. It's a kind of comparison that we will draw between these two domains. So let's consider a mechanical network. It is relatively a simple mechanical network with a spring and damper connected in parallel to a mass M. Here D is damper, K is stiffness of the spring. We have a displacement in the x direction when a force is applied on this mass. This force is applied externally to displace this M with a displacement x. Now every component that is connected in this network will try to oppose the applied force to make itself in the equilibrium. So we will derive these equations based upon law of conservation of energy. So applied energy is F equal to m x double dot, where double dot stands for second order derivative. Similarly, we have another damper and it will oppose with the dx dot magnitude, where x dot is the first derivative of displacement. And the third component is spring, which will oppose based upon its Hooke's law, where K is the stiffness of the spring, D is the damping factor in this damper, M is the mass of this, M is the mass that is available in this network. So let's transform it into the frequency domain, where we will use the M Laplace domain. So ms square x of s plus ds x of s plus k times x of s. Now we have transformed this network into the frequency domain. So we will further elaborate it with the electrical network and we will compare both equations. So consider this as equation number 1. Now let's define our second equation, and this is based upon the electrical network. It has three components. One is the resistor, the other one is the inductor, and third one is the capacitor. Then I current is flowing in this network. R is the resistance, L is the inductance, and C is the capacitance of this network, where V in is its applied voltage. So following the same principle, we will utilize the mesh analysis in terms of log conservation of energy, that the energy that is supplied to the network is equal to the opposition energy or the energy consumed by the network. So similarly to the mechanical network, where we have used a mechanical system, and here each component was opposing the applied force, and it was opposing it in the opposite direction. So that's why all the quantities are on the right hand side to the applied force. Similarly, when we apply the same energy in terms of V in to this network, which is electrical network, the equations will be similar in the form. Let's say here the position by the resistor is defined as IR, and inductance position is defined as di by dt. Here I am using the full script compared to the earlier equation, where first derivative was symbolized with a single dot. Here I am writing it di by dt. They are same. Plus 1 by c integral of I dt. As we know that I is equal to dq by dt. So using this equation, in this earlier equation that we can call it 2a, now using I's definition in equation 2a will change and will contain the charge factor. So after getting this equation 2b, now let's transform this same equation into the frequency domain. So for this 2b in frequency domain, using the Laplace definition, we will get r s q function of s plus l s square q function of s plus q, which is a function of s, divided by c. So this is our transformed equation and we call it equation 2c. Now if we are going to compare this equation with the earlier equation that is written for the mechanical system, and it can be rewritten as f of s, which is applied force, and we want to write it with the compatible with the equation 2c. So we will rearrange the quantities there and we will write ds x of s plus m s square x of s plus k times x of s. So if you're going, let's give it a name and 1a. If we can compare this equation 2c with equation number 1a, we can find that they are both have the second order polynomial, and the polynomial then descends to s and s naught. So if we are going to compare 2c with the 1a, we can find that there are a few quantities which are constants there, which are their coefficients. They can be compared, like the first one is d, and here we have a r. So d can be compared with the r. They are both analogous to each other. Similarly, we have another component that is m, and compared to this one we have a inductance. M is analogous to L, which is inductance. Similarly, the last quantity here is q, and we have 1 by c is the coefficient of q of s here in the equation 2c. So k is analogous to 1 divided by c. To further reform our analogy, we can see a simple relation that voltage across the inductor produced due to the change in the current can be defined as, for inductor, V is equal to L d I by dt. It can be rewritten as V by L is equal to di by dt. So change in current will induce the voltage. Now in case of mass, we know that by showing the dynamics in mass as its tendency to show the opposition in change is defined by Newton's third law, and it is equal to A is equal to F by M. Normally we write it F is equal to MA. So I have rearranged this equation so that our comparison with the earlier equation of the inductor can be modeled. So we know that A is nothing but the change in velocity, and if it is equal to F divided by M. So now we can compare these both equations. Here change in velocity has caused the opposition in mass, and change in current causes the voltage induced by the inductor. So this is another way to compare the analogy between to define the analogy between the inductor and the mass. Similarly, for the damper and resistor, Now we have equation for the resistor following the Ohm's law. Where V can be further defined in terms of the charge as dq by dt times R. For damper, we know that due to friction force, Fd is equal to d times V of t, which is the velocity compared to the voltage here. Now d velocity can be further defined as dx by dt. Now again we can compare that V by R is equal to dq by dt, and here we have F d, which is the damping force, divided by d, which is the damping coefficient, equal to dx by dt, which is the velocity factor. So velocity, the change in displacement depends upon the applied force, damping force, and its ratio with the damping coefficient. Similarly, for the change in current, we can expect a voltage drop. For the spring and capacitance, we can see that spring, which has a model like this one, and capacitor, which has the model like this one, we have the applied energy in terms of voltage at capacitor, and we have applied energy in terms of force in across the spring. So we can define its stiffness as K and its displacement as X. So what will happen that if K is high enough, then it will oppose the displacement X, right? So the more the K, the more the opposition that we can expect from this spring. So following the Hooke's law, we can write F is equal to K times X. So it depends upon the stiffness coefficient of spring K, that how much energy it will introduce to oppose the applied force. So let's call it Fk, so that we can discriminate between the applied energy and the opposition energies. Similarly, for this network, which is electrical network, the Q, which is a charge stored across it, depends upon the product of C and the applied voltage V. So Q is equal to V divided by 1 by C. So here we can, if we are going to compare, or for the proper comparison, let's write this equation in terms of X, which is Fk divided by K. So if we are going to compare this X with the Q, which are both states of the system, that their relationship is like similar to each other. Only difference is that K is inversely related to the capacitance. So this is the whole analogy between the components of electrical network and the mechanical network. Hopefully you can find the analogy between the electrical and mechanical components, so that our concepts that we have developed for the electrical network could be utilized in the mechanical network. Take care of yourself till the next video. Hopefully we will back with some more content. Take care.